Hey guys, this video is over chemical kinetics and the integrated rate laws and how they work. It might be useful to go ahead and get out your formula chart that was given to you so you can look and see what's given to you on the AP test and compare it to what's in this video. Alright, so the integrated rate laws, these give you the ability to calculate the concentration of a reactant at a later time in the reaction. So, as a reaction goes forward to completion, the reactants are going to be disappearing and the products are going to be appearing, right? And they come from taking the differential rate law, which is just the basic rate law that we've been talking about, and integrating them with respect to time. Obviously, calculus is not a prereq for this course, so we're not going to have to get these laws, but you do have to be familiar with them and know their names. So that's I wanted to tell you how they were obtained. All right, so the integrated rate law for first order, right? This is first order because there's a 1, an invisible 1, as an exponent to A here. And so the integrated rate law for that looks like this. So if you look closely at this, you'll notice that it has the same form as y is equal to mx plus b, where the natural log of A naught is equal to the y-intercept, and we're putting the natural log of A at time t on the y-axis, and time is on the x-axis, and so the slope would be equal to negative k. And I know that is very abstract right now because you haven't seen any of this and you don't know what any of that means, but I'm about to explain it, so just give me just a second. All right, so these zeros here means that it's happening at time 0. So time 0 is when the reaction first starts. It's what you put into the reaction container. So these brackets mean concentration, and that naught means initial. So this basically means initial concentration of A. All right, and then we see this one here, and that means concentration of A at time equal to t. So whatever time we put in here for x, the concentration of A has to be at that particular time. All right. And so K is still the same rate constant that it always was. And then the natural log is a button on your calculator. So then if this is y, that's what's on the y-axis for first order, right? So this is y versus x for first order. So we would have natural log of A versus t, and this would be at every single corresponding time. And so we would get a graph that looks like that, and it would be linear because y equals mx plus b is for a straight line. All right, and then we have the same thing for a second order, except we don't have negative k and we don't have natural log. We have the inverse of A. So still we have y is equal to mx plus b. So this is our y-intercept. It's 1 over the concentration of A initially. So the very first concentration that we put in. And then y is the inverse of all the concentrations of A at every time that we put on the x-axis. And then the slope is equal to k. And then the very last one is for 0 order, and this is one of the weirdest ones to understand in my opinion, because the concentration of A has 0 effect on how fast the reaction goes. So 0 order, we actually have A raised to the 0, and anything raised to the 0 becomes 1, so that goes away. And so the rate is unaffected by our concentration of reactant. So we still have y is equal to mx plus b, and the y-intercept is going to be the initial concentration of A. We're going to plot all of the A values on the y-axis that correspond with the particular times that we put on the x, and then the slope is equal to negative K. And so these are really kind of easy to memorize because they all take the same form where we have A at time t on y. It just depends on how we manipulate A at time t. So here we take the natural log, here we do the inverse, and here we just, it's just A. And we can find the slope of the line, and it's always going to be equal to K. And so the way that you can remember that is it's always going to be the positive number. So if you have a negative slope, you just change the sign. If you have a positive slope, then that's the K. All right, so we'll look at a few examples of this so that hopefully it kind of clicks. Okay, so we have some data here, and we're looking at this reaction right here. And so the only reactant we have here is dinitrogen pentoxide, and here's all of the concentrations, right? So this would be A naught because it's the A at time 0. And then these are all different values of A at different times. So this would be A at 50, this would be A at 100, and so they're all A's at time t's. And so for this right here, for this first graph, we've got the concentration of dinitrogen pentoxide, and so at time 0 we have 0.1, and that's this data point right here. So this is on the y-axis and this is on the x-axis. And then the next point is 0.707, and that's at time 50, and then time 100, and then time 200, right? It's just a little over 0.02. So we plot all those points, and since this right here, right, since it's not a straight line, and this would be for 0 order, because 0 order would be just the concentration of A at time t versus time. Since it's not a straight line, it's not 0. It's not 0 order. And then we have, right here, we have the natural log of N2O5 versus time. So that's for 0 order. So basically what they did was they took the natural log of all of these values and they plotted it, okay, all the way down. So they found these values and plotted it right here. So if you were to take the natural log of 0.1, you would get it to be about negative 2.3 or something like that, negative 2.3 right here. And so that's where they got that first point. They just took the natural log of 0.1. And when we graph it, we get a straight line. It's straight. And since this one has the natural log of N2O5, then that means that this is first order. So the reaction is first order with respect to N2O5. We know it's not second order because 1 over A at time t versus the time is not a straight line, it's a curved line. So since it doesn't give us a straight line, it's not second order. So it has to be first order, and it says to calculate the value of the rate constant. Well, I have the line right here, okay? And so my slope is equal to negative 0.0069, and so my rate constant is going to be 0.0069, and since it is first order, it's going to be inverse seconds. Okay, because our time is in seconds, and since we're doing the natural log on this, right? So it's y, the slope would be y, change in y, over change in x. Okay, these natural logs, they don't have any units, and then we have seconds here on the bottom, so it's inverse seconds because our x values are in seconds. All right, and it says using the data given in the question above, calculate N2O5 at 150 seconds after the start of the reaction. So since we know it's first order, we've got this equation, and you should have this written down from the page before. Okay, and I will plug in my values of K, which is 0, and don't forget your negative sign because it's right here, 0.0069 inverse second, so 1 over a second. And then my time is 150 seconds plus the natural log of A naught, which is 0.1. So if I multiply these first two here, and then add the natural log of 0.1, I get negative 3.338. And that's going to be equal to the natural log of N2O5 at time t. So I need to get rid of natural log, and then the way that I do that is I use E, right? That second natural log on your calculator. So that gets rid of this. And E raised to the negative 3.338 would tell me that A at time t, or N2O5, because that's the reactant that we're looking at, is equal to 0.0355 molar. And so one thing that I do, since 150 time goes between these two, right, then we should think that this concentration here should be between there, and it is. All right, so before we continue this, most of the questions on the AP test are half-life questions, so I want to make sure that we understand half-life before we continue through this. It says the half-life, which is represented by this right here, T 1/2, is the amount of time that it takes for the reactant to reduce to half of the amount it started at. So if we have 100 grams, after a half-life, we would have 50 grams. So if it goes through 2 half-lives, how much is left? So if we start at 100% and we go through 1 half-life, then we would have 50%. And then after another half-life, we would have 25%, right? And then after a third half-life, we would have 12.5%. And so it just continues on from there. Okay, and so each half-life equation is slightly different, and I'm not going to go through how these are obtained. If you'd like to see that, you can ask me in class. I'll be happy to show you. But this is the only one that's on the AP test. All right, it's the only one mentioned in the big ideas. So we're not going to really talk too much about these other ones. I might do some example problems with them to kind of change it up so it's not so obvious all the time. But then in college, we definitely do use 0 and second order. So don't think that it's just not important, because it is. But if you look at this half-life equation, it's the only one that doesn't have the concentration of A in it, right? So that means the half-life is completely independent of the concentration of A for first-order reactions. Here it matters how much you start with. Here it matters how much you start with. But for half-life of a first-order reaction is independent of the amount you start with. Okay, and so it says the only half-life equation that is not concentration dependent is first order. So everything else is really the amount that you start with determines how long the half-life is. Remember, that's not the same thing as we were talking about earlier with zero-order reactions. With zero-order reactions, the rate is independent of the concentration of your reactants. That's not the same thing as the half-life being independent, because the rate is not independent of the concentration of your reactants here in first-order reaction. It's only the half-life. All right, so example 1. A certain first-order reaction has a half-life of 20 minutes. So it says it's first order, and the half-life is 20 minutes long. Calculate the rate constant. So the first equation here is going to be the half-life is equal to 0.693 divided by K. So I know that my half-life is 20 minutes. And that's 0.693 divided by K. Multiply by K on both sides. K's cancel out over here, and so I end up with 20 minutes times K is equal to 0.693. Divide both sides by 20 minutes. And we end up getting that K is equal to 0.0347 inverse minutes. How long will it take to get to 12.5% of the starting material? Now for this, you could use this equation Okay, where you could start off with 100% here, go down to 12.5 here, solve the equation for time, and that would work. But you don't have to. So if I look for first order reactions, the half-life is always the same amount of time. So it says right here that the half-life is 20 minutes long. So let me write that up here. For first order reactions, the half-life is always the same amount of time. So for this reaction right here, if it's 20 minutes for the first half-life to pass by, the second half-life is going to take 20 minutes as well because it's independent of concentration. All right, so I'm going to say if I have 100% that I'm starting with and I go through one half-life, then I would have 50% because that means half of it is gone. Then I'm going to go through another half-life, and that means that I would end up with 25% because half of 50% is gone. Then I go through another half-life, and I get 12.5% because half of 25 is 12.5. So that means I've gone through 3 half-lives, and each half-life is 20 minutes. So 3 half-lives, 20 minutes, that means that 60 minutes it will take to get to 12.5%. All right, let's do another example. Okay, so it says butadiene reacts to form a dimer according to this reaction. So here's a reaction. The data on the right were collected for this reaction at a given temperature, and the graph is shown below. Is this first, second, or zero order? So we're going to look at the one that yields us a straight line. So here, this would be for zero order because it's just concentration of A versus T. This would be for first order because it's the natural log of A versus T. And this one would be for second order because it's 1 over A versus T, right? All I'm doing is looking at the y-axis to get that information. And so because this one gives us a straight line and this is for second order, this reaction is second order. And the value of the rate constant is always going to be a positive slope. This already is positive, but that would be K. So the slope here is going to be, the rate constant is going to be 0.0612. The units are going to be 1 over molarity times the second. All right, and that's because, remember, slope is found by change in y over change in x, and my change in y, my y values are 1 over molarity, and then I have seconds on the bottom, so that equals 1 over m times a second. All right, so that's just y over x. That's how you find the slope, right? Change in y over change in x. Okay, what is the half-life for the reaction under the initial conditions of this experiment? So the equation for the half-life of a second order reaction is 1 over A naught times K. That's equal to the half-life. All right, so hopefully you have that written down. And so my K is 0.0612. So I'm going to put 1 over 0.0612. And then I've got A naught, which is 0.01. Right, I just get it right here. So that's my first concentration. And remember, this is 1 over molarity times the second, and this one is molarity, so molarity cancels out. Seconds goes into the top. So if I take 1 and divide it by the product of these two, I end up getting that my half-life is equal to 1633.98, which is 1634, and it would be in seconds. All right, so let's go to the next one. So it says we have a general reaction here, and at a particular temperature, we're starting out with 2 times 10 to the negative 2 versus time were collected for this reaction, and a plot of the natural log of A versus time results in a straight line. So since the natural log of A versus time is a straight line, that means it's first order. And the slope value is negative 2.97 times 10 to the negative 2. So A, if we determine the rate law, we know that it's first order. So B rate is equal to K times the concentration of A, because that's my reactant. and it's to the first order, so that's it. The integrated rate law would be the natural log of A at time t is equal to negative kt plus the natural log of A naught. And the value of the rate constant is going to be the positive value of the slope. So K is equal to 2.97 times 10 to the negative 2 inverse minutes. The half-life of the reaction is going to be 0.693 divided by K. So if I plug in my K value, 0.693 divided by 2.97 times 10 to the negative 2 inverse minutes, that is equal to 23.3 minutes. Okay, that minutes, because you're dividing by a fraction, remember fractions get flipped. So minutes comes up to the numerator. All right, so this last problem says how much time is required for the concentration of A to decrease to 2.5 times 10 to the negative third molar. All right, so we want it to get down to here and we're up here. So there's two ways you can solve this. One, you have to be able to see factors really well, and not just factors of whole numbers, but factors of fractions. So not all of us are good at that. So I'm just going to show you the straightforward way, and that is to use the integrated rate law. Oops. So that should be A at time t is equal to negative kt plus the natural log of A naught. And so if we plug the numbers into that equation, right, then we would have the natural log of A at time t would be this, because we're looking for how long, how much time. So it'd be 2.5 times 10 to the negative third, and that's going to be equal to negative k, and the k is 2.97 times 10 to the negative 2 inverse minutes, and we're looking for time, plus the natural log of A naught, which is 2.00 times 10 to the negative 2 molar, right? Okay, so if we go through this and we do the natural log thing to both sides for both of those, I'm basically going to take this and bring it over here. And you can do this either way. You can turn it into numbers where you're not dealing with the natural log on both sides. So that would cancel out. And I'm going to take this and subtract that from it. So this shouldn't be a 3, it should be a 2. All right, and then I end up getting negative 2.07944. And that would be equal to negative 2.97 times 10 to the negative 2 times t. Right? Then I'm going to divide both sides by this one, divide by that on both sides, and I end up getting that my t is equal to 69.9 minutes. So if I look at what is actually happening here, and I take 2.00 times 10 to the negative 2, which is my A naught, and I divide it by half, right? So I find the first half-life. I end up getting 1 times 10 to the negative 2. And then if I divide it for a half-life again, I get 5 times 10 to the negative 3. So you can put in your calculator this one divided by 2, and you get that. And then you can put in your calculator divided by 2, and you get that. So I'm going to do it one more time, and I get 2.5 times 10 to the negative third, which is this value right here. So it went through 3 half-lives. So if a half-life is 23.3 minutes, if we multiply that by 3 half-lives, we get 69.9. Okay, so there's two ways you can do it, but this one you have to pretty much notice that that's what's happening. I will tell you that on the AP test, usually you can use half-lives. I have not seen them do anything like this in a very, very, very long time. All right, let's do some more examples. All right, example 4, a certain reaction has the following general form at a particular temperature, and at a particular temperature, and A naught is this, the concentration versus time data were collected, and the plot of 1 over A versus time resulted in a straight line. So that means that it's second order. And the slope is this, so that would be K, right? And it says determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. So the rate law, since it's second order, it's going to be rate is equal to K times A squared, because it's second order. And the integrated rate law is 1 over A at time t is equal to KT plus 1 over A naught. And then the rate constant is equal to 3.60 times 10 to the negative 2, and that's inverse molarity times a second, liters over mole second. Okay. B, calculate the half-life. And so what we determined was that the half-life equation is 1 over K times A naught. So if I plug those things in, 1 divided by 3.60 times 10 to the negative 2, that's my K, times A is 2.80 times 10 to the negative third. My half-life is going to be 9,920.6 seconds. How much time is the concentration of A to decrease to 7 times 10 to the negative 4? So for this one, I'm going to plug it into the integrated rate law right here, where this value will be A at time t, because that's the time that that's the concentration we want it to be at time t. And then this is my initial concentration. And so my K, 3.60 times 10 to the negative 2. And then my time is what I'm looking for, plus 1 divided by 2.80 times 10 to the negative third. Okay, so if I put into my calculator 1 divided by 7 times 10 to the negative fourth minus 1 divided by 2.8 times 10 to the negative third is equal to 3.60 times 10 to the negative 2. So all I did was subtract this from both sides. So if I put this in my calculator and subtract that, I end up getting 1071.43, and that's going to be equal to 3.60 times 10 to the negative 2 times t. So I'm going to divide by this. And I end up getting that my time is going to be 29,761.9 seconds. All right, so sig figs and stuff, you'd have 29,800 seconds. All right, I've got a couple more examples here, so let's see what they are. Okay, so what is the length of the half-life shown in the graph? Okay, so this was on a test recently, something just like this. So really pay attention here. Not on one of my tests, but on the AP test. All right, and so if we want to know the length or the time it takes for the half-life shown in the graph, so if this is where 1 is, that's the concentration, then we want to look and see where 0.5 is. And so here's 0.4, here's 0.6, so 0.5 would be right here. And so the half-life is 15, and it's in seconds. So the half-life is 15 seconds. Right, and then it says, what is the value of K? Right? So if I look for the next half-life where 0.5 is, and then 0.25 is going to be about right here, it's 30 seconds. And so since each half-life is taking the same amount of time, that means that it's first order. Okay, so since each half-life takes the same amount of time, it's first order. And that's why we couldn't use, on the problem before that we just did, we couldn't use half-lives to figure out what time we would get there, because it actually went through 4 half-lives if you look at it. That last problem that we did on the last slide, but we couldn't use the half-lives for that because it's second order, and so second order reactions, each half-life takes a little bit longer than the last. Actually, I think it went through 3 half-lives. I don't remember, but it says since each half-life takes the same amount of time, it's going to be first order. So the first order equation, 0.693, right, divided by a half-life is equal to K. So if I just put my half-life in here, that means that I have 0.693 divided by 15 seconds is equal to K, and so my K is actually going to be equal to 0.0462 inverse seconds. And it says, what is the concentration of the reactant after 90 seconds? So we can't see 90 on here, but if I know that every single half-life takes the same amount of time, then how many half-lives will it go through, right, to get to 90 seconds? So 90 divided by 15 is 6. So it will take 6 half-lives, right? So I'm going to take my concentration and I'm going to divide it by 2. That's my first half-life, and I get 0.5 because I started off at 1 molar. That's why I started with 1 right here. Then I'm going to divide that by 2, and I get 0.25. And then I'm going to divide that by 2, and I get 0.125. And then I'm going to divide that by 2, and I get 0.0625. And then I'm going to divide that by 2, and I get 0.03125. And then my last one is that, and so I get 0.015625 or 3. So it went through the first, the second, the third, the fourth, the fifth, and the sixth half-life. And so this one takes 15 seconds, and then this one takes 15 seconds, and then this one takes 15 seconds, and this one takes 15 seconds, and this one takes 15 seconds. Did I miss one? 1, 2, 3, 4, 5. And then this one takes 15 seconds. So every single one of them takes 15 seconds. And if you add all this up, that would be 30, 60, and 90 seconds. And so that's why it's that. All right, next. It says the first order reaction is 75% complete in 320 seconds. What are the first and second half-lives for this reaction? So if it's 75% complete in 320 seconds, that means there's 25% remaining if 75% is complete, right? So that means it's gone through 2 half-lives. So for 2 half-lives, that means that it takes 320 seconds. So for 1 half-life, it should be half of that, 160. And each half-life is 160 seconds. Next. It says the rate law for the reaction of this is this. If the half-life of the reaction is 2 seconds, when NOBR is 0.9, calculate the value of K. All right, so, and then how much time is required for the concentration to decrease to 0.1? All right, so if I look right here at this, right, that means that it's first order because there's no exponent, so the exponent can only be 1. And so to find K for that reaction, if the half-life is 2 seconds, then my K is going to be equal to 0.693 divided by 2 seconds. And so my K is equal to 0.347 inverse second. And then how much time is required for the concentration of NOBR to decrease to 0.1? So we're going to use the integrated rate law and plug everything in. So my A at time t is going to be 0.1, and my initial is going to be 0.9. So the natural log of 0.1 is equal to 0.347, and that has to be negative because of that. Looking for that amount of time that has to pass, plus the natural log of A naught of 0.9. All right, so if I bring this over, I end up getting negative 2.197 is equal to negative 0.347 times t, divide both sides, and my time is equal to 6.34 seconds. All right, that's it. We'll do some practice in class. If you've kept up with this video and watched it and understood what was happening through 60% of it, then you should be good. So go back and watch parts that you were unsure of, or ask questions, or email me, or read in your textbook, or look at other videos, or whatever you have to do to get it down so we can get some hands-on stuff done in class.